All right, geometry students, our 9-1 lesson is pretty straightforward, so I'm going to kind of fly through it. So our first theorem is just the Pythagorean theorem, which you should definitely know. This just says in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So that's just our very famous a squared plus b squared equals c squared statement. You might have seen this before. Here's a core concept. It's just showing you some common Pythagorean triples and their multiples. So the most common Pythagorean triples are these ones bolded on the top: 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. And then any set of three whole numbers that are all multiples of these very common triples will also work to create right triangles. That's all this statement is saying. So these first ones, it says find the value of x, tell whether the sides lengths form a Pythagorean triple. So if we go ahead, don't get this one confused with a 3, 4, 5 because the x is our hypotenuse. So we would do 4 squared plus 5 squared equals, I always say c squared, we probably should put x squared. Sorry, this looks like a 6, so 5. So we'd have 16 plus 25 equals x squared. So x squared equals 41, which means x equals the square root of 41, which is not going to be a whole number. So this is not a Pythagorean triple because the length of our hypotenuse is not a whole number. Okay. Example 2, find the value of x, then tell whether the side lengths form a Pythagorean triple. So we're looking for a missing leg. So 15 squared plus x squared equals 25 squared. So this is 225 plus x squared equals 625. Subtract 225 from both sides. I get x squared equals 400, which means x, if we take the square root of both sides, x would equal 20. And then it says, so this is, yes, this is a Pythagorean triple. And if you notice, 15, 20, 25 are multiples of the 3, 4, 5 Pythagorean triple. Okay, a little word problem here. It says the flagpole shown is supported by 2 wires. Use the Pythagorean theorem to approximate the length of each wire. So if I look at this, I see that we are missing the length of a leg. We only have to do this for, I'm sorry. We're not missing the length of a leg. We're missing the length of the hypotenuse. We know that the leg is this 15.1 feet over here. That's the height of where the wires hit the flagpole. So we have 8.5 squared plus 15.1 squared is going to equal our x squared. Hold on a second. I'm going to have to pull out a calculator for this one. So 8.5 squared is 72.25 plus 15.1 squared equals 228.01. So if I add those together, I get 300.26. And then if I take the square root of both sides, I end up with x equals roughly, approximately 17.33. So obviously, this is not a Pythagorean triple because there aren't whole numbers involved here. So, okay. So here is the last theorem, I think. Oh, wait, I think we have one more, actually. So the converse of the Pythagorean theorem, which, again, you should already know this to be true, that if the square of the length of the longest side is equal to the sum of the length of the other two sides, then the triangle is a right triangle. So if we know a triangle is a right triangle, we know about the side lengths. If we know that the side lengths squared equal the longest side length squared, then we can determine that this is a right triangle. That's what that's telling us. Okay. So it says tell whether each triangle is a right triangle. Again, this is not anything new. So if you look, 12 would be the longest side here. So I have 8 squared plus 4 to the square root of 5 squared equals 12 squared. Well, 8 squared is 64. 4 to the square root of 5 squared means 4 square root of 5 times 4 square root of 5 equals 144. If I simplify this piece here, I'm going to go over to the side so I have a little bit more space. I'm going to think about this as 4 times 4 times the square root of 5 times the square root of 5. So just using the commutative property to rearrange that. So I have 16 times the square root of 25. If you think about it, the square root of 5 times the square root of 5 is just going to be a whole number, right? It's going to be 5. So if you want to skip this step that I just took, that's okay. So it's 16 times 5, which would be 80. So I have 64 plus 80 equals 144. So yes, this is a right triangle because that is true. Okay, and the next one here, let's see, 9 squared plus 2, the square root of 30 squared needs to equal 14 squared. So that's 81 plus 2 times 2 times 30. Kind of skipping that step. I can show you that again in an example if you need to know how to do it. So 30 times 2 times 2, so 81 plus 120 is not going to equal 196. So this is not a right triangle. And then the last one here says, this Pythagorean inequalities theorem says for any triangle ABC where C is the length of the longest side, if C squared is less than A squared plus B squared, it's an acute triangle. And if C squared is greater than A squared plus B squared, it is an obtuse triangle. So it says verify the segments of the lengths 14, 15, and 11 form a triangle. Is it acute, right, or obtuse? So I have 11 squared plus 14 squared would be, I'm just putting this in my calculator, so 11 squared plus 14 squared would be 317. 15 squared is 225. So since A squared plus B squared is greater than C squared, that means this is or that C squared is less than A squared plus B squared. This is an acute triangle. And if you'd like to, you can try the exit ticket, but it's not required.